Good morning, students. So, in this class, we will learn how to develop or how to find the dual of the primal problem. So, the theoretical part is covered in the previous lecture, and now the numerical example we will do here. We will clearly understand how we can find the dual of various kind of primal problems. So, first question, construct the dual of the following problem. This is my problem. All the constraints are less than equal to type and objective functions of maximization type. So, as studied earlier, what will be its dual? The primal dual objective function will be of minimization kind. These columns will become row. Okay, the coefficients in the objective function will be the right hand side of the dual constraints, whereas the right hand side of primal constraints will be the objective function of the coefficients of the objective function of the dual. So first of all, first task here is just to define the dual variables. Now how many dual variables will be there? Those will be equal to number of constraints in the primal. So 1, 2, 3, 4, 4 constraints. There will be 4 variables. So let y1, y2, y3 and y4 be the dual variables. Then the dual of above LPP problem is minimize z dash. So I can denote this z dash or zd or z star, because this objective function is not different from the earlier one. That's why we have to give a different symbol to this objective function. So I have given here z dash. So minimize z dash is equal to 50y1 plus 35y2 plus 10y3 plus 20y4. As told earlier, we can see the right hand side values will be the coefficients of the objective function of dual. Okay, similarly the constraints, now there will be 2 constraints because here are only 2 variables. So first column will represent the first uh, dual constraint, 2y1 plus 3y2 plus 5y3 plus 0 into y4. So greater than equal to 3. 3 means this one, this value, coefficient of objective function in the primal. Similarly, we can find out the second constraint, sigma y1 plus 2y2 minus 3y2 plus y4 greater than equal to 5. And all these y1, y2, y3, y4 greater than equal to 0. This is how we found the dual of primal problem. Okay. So find the dual of the following LPP. So minimize z is equal to 3x1 minus 2x2 plus 4x3, and subject to these 1, 2, 3, 4, 5 constraints. Out of these 5, only one is of less than equal to type and all other are greater than equal to type. Okay. So what should be there? What is the requirement? That if the objective function is minimization type, all the constraints should be of greater than equal to type. So this is not of greater than equal to type. What we can do, we can simply multiply throughout this left hand and right hand side, and we can change the sign of this inequality to greater than equal to type, and this will be minus 10, minus 7, 2 plus 2x2 plus x3. Okay, so first task is this, so that I have shown roughly here. So all these are of same type now, and after that we can find out the dual. So minimization type of objective function, the primal, dual will be of maximization type. First, what are the variables? Since there are 5 constraints, so there will be 5 variables in the dual. Let these be the variables. Then these coefficients 4, 7, minus 10, 3, 2, these are the right hand side values of the primal constraints, and these are like this: 4, 7, minus 10, 3, 2. So that's how we have written it. And subject to the constraints, so there are 3 constraints because there are 3 variables in the primal, and column wise we will start. So this will be first row, 3y1 plus 6y2 plus 7y3 plus y4 plus 4y5. So we can see here all. And similarly with the second column and with the third column, we can write the left hand side of these constraints, and all the signs of inequalities will be reversed. Minus less than equal to, less than equal to, less than equal to, right hand side values will be the coefficients of objective function in the primal, 3, minus 2, 4. So 3 minus 2, 4. So this is the, this is the dual of the given problem that we just obtained. And third one, here I am taking a different kind of constraint that is equal to type. And how to handle this kind of constraint. Okay, this kind of constraint is converted into two more constraints, one with the same data, one of less than equal to type, other of less than equal to type. So first writing the second constraint as 3x1 minus 2x2 plus 4x3 less than equal to 3, and 3x1 minus 2x2 plus 4x3 less than equal to 3. It means the same thing. Okay, so now this is of greater than equal to type. This has to be made of less than equal to type. So simply again converting this less than by multiplied with minus sign. So minus of 3x1 minus minus plus 2x2 minus 4x3 less than equal to minus 3. So these are now my constant. One this, other this, all these are of less than equal to type, objective function maximization type. So now we can find out the dual. Okay, let y1, y2, y3 be the dual variables, then minimization of z dash is equal to 7y1 plus 3y2 minus 3y3. So 7, 3 or minus 3, these are coming from the right hand side of the primal constraints. And similar way we can write on these constraints. Okay, the columns become rows. Okay, like this. So we can write all these now in the dual. All the constraints will be of equal to type. And these right hand side values are from here. Here the coefficients of variables in the objective function 3 times 2. So this is 3 times 2. Now again 3 times 2. Again we can simplify it. So we can take 3 common in the objective function, 3 common if I take y2 minus y3, 3 common if I take in the constraint y2 minus y3, 2 common if I take y2 minus y3, and if I take 4 common, so y2 minus y3. So I can write this problem like this. Now this y1 minus y2 can be written as a different variable. Okay, let this be denoted by y2 dash. Okay, so if I denote this by y2 dash, I get this problem. Minimize z dash is equal to 7y1 plus 3y2 dash, 2y1 plus 3y2 dash greater than equal to 3, 3y1 minus 2y2 dash greater than equal to 10, 2y1 plus 4y2 dash greater than equal to 2, where y1 is greater than equal to 0 and y2 is of unrestricted in sign. So what is the meaning of this unrestricted in sign? Now coming here. Okay, now this is y2 dash. What is this? This is a difference of two positive variables y2 and y3, but we are not sure about which is greater than which. If y2 is greater than y3, then the sign of y2 dash will be positive. But if y3 is greater than y2, then the sign of y2 dash will be less than equal to 0. Less than 0. So that is, we are not sure about the sign of y2 dash. That's why we call it unrestricted in sign. And there is a theorem of duality also, which states that if ith variable is of equal to type, then ith dual variable will be of unrestricted in sign. So in the same problem, if we see the second constraint was of equal to type, and hence here we can see that the second dual variable y2 dash is of unrestricted in sign. Okay, so this is how we handle all these mixed kind of signs or mixed kind of constraints and various variations. Okay, so we learned in this small lecture that how to find